So we're looking at springs now. So guys, we know that when we happen to take a spring, either we pull it or push it. What happens? It forces us back. Okay, is it not? So let me take a spring. And we have, say, consider this to be some weightless stuff. So it is for the grip. Now, if we happen to compress this, what happens? If we happen to compress this, what happens? The spring will apply a force, yes, in the right direction. Do you guys agree? So this is the direction of my applied force. If I happen to pull the spring, I should be doing a better job. If I happen to pull the spring in this manner, right? If my applied force is to the right, what happens? The spring will pull it to the left. The direction of the spring will be to the left. Do you guys agree? So basically, when I do all of this interaction, there is energy stored, is it not? When you compress a spring, there's an energy stored. Like when you click a pen, right? When you click the pen, what happens? First, there is energy stored, and when you click it again, that gets released and it comes out. So that is nothing but your energy stored. That is nothing but your potential energy. This is because of the spring. So when you stretch or compress a spring, you're doing work on it. You're putting energy into it. This energy does not disappear. It gets stored up in the spring like a tension in the rubber band. We call this a stored up energy of the spring. That is your potential energy of the spring. There are a few points that we need to observe. Equilibrium position, direction of the displacement, and the force. Now, equilibrium position is a position wherein the spring is not applying or does not store any energy. So which case is that? Is it case A, B, or C? Right. Case A is your equilibrium position. When there's no force applied, right? When the net force is zero. Not net force is zero, but there's no external force. EXT actually, external. When the external force is zero, we have the object at a particular point, and that is your equilibrium position. Next thing is the direction of the displacement and the force applied. If the direction of the displacement is to the left, the force is to the right. If the direction of displacement is to the right, the force is left. Okay, so this is your direction of displacement. This is your direction of displacement. Next is what? Mathematical expression. So as per Hooke's law, the spring force is proportional to displacement of the block from the equilibrium position. So we have a very simple formula. The force that the spring will exert will be equal to or is proportional to the displacement. So that's your Hooke's law. H-O-O-K-E-S, Hooke's law. I think it is right. H-O double only. Okay. It's proportional to this. When I remove this proportionality constant, I need to take into account a negative sign, and sorry, when I remove the proportionality symbol, I need to consider proportionality constant. It's not 1 over here, and we need to consider the negative sign. So negative sign is indicating that the direction of the force is always opposite to the direction of the displacement. Direction of force by the spring. Spring force, basically. Direction of spring force. Is opposite to direction of displacement. And we have this, that is your spring constant. So this value depends on the spring material and all that. Depends on the material of the spring, and there are quite a few factors, but yeah, spring material on the depends on the springs, many factors actually. But anyways, we don't have to bother with that. We just have to bother. They'll give the value. We just have to take care of it. Okay, guys. Now, if I happen to, since it's directly proportional, if I happen to put it across on a plot, so this is x, and this, if it is f of s, okay, then our plot or graph will look something like this. So this is negative k times of x. So when x is positive, force is negative. When x is negative, force is positive. That is, it is pointing towards the right. Okay, so yeah, I think the graphical view, I've done all of that. And to observe in the graph that force is negative in the positive x-axis and force is positive in the negative x-axis. That I made a point. Okay, so now you have to copy this. The mathematical expression is over here and the graph is on the left.